Here we want to solve this system by substitution. So the first step is to isolate one of the variables. Let's look at the first equation, and let's just go ahead and isolate the y. Subtracting 2x, negative 5y then would equal negative 2x plus 3, then dividing by negative 5. On the left side, these negative 5's will cancel, you get y equals. Okay, and remember, you got to divide both of these by negative 5, so 2/5, because those negatives will cancel, 2/5 x minus 3/5. So the first equation can be written in the equivalent form, y equals 2/5 x minus 3/5. So then take that y and substitute it into that second equation there. This is the substitution step. Okay, 4x minus 10 times y equals 6. For y, I'm going to substitute 2/5 x minus 3/5. Now don't be afraid of those fractions, it's really no big deal. Here you're left with 4x. Now negative 10 times 2/5. 5 goes into 10 twice, so that leaves me with negative 4x. Then negative 10 times negative 3/5 will be plus 5 goes into 10 twice, 6. Okay, so certainly you could do this on the side. 10 times 2/5 is 4. 10 times 3/5 is 6. Now you have same side like terms. 4x and negative 4x is 0, so that leaves me with 6 equals 6. Now look at this. The math is giving me an identity here. Gave me a true statement. So what's that telling me is that there's going to be infinitely many solutions. Geometrically, that means these two lines were actually the same line. And we know when we have this dependent system, the infinitely many answers can be written in set notation, x comma y, but instead of y we put mx plus b. Okay, so in our case, the set of all solutions here, x comma our particular mx plus b, is 2/5 x minus 3/5. Okay, so infinitely many ordered pair solutions where x is the independent variable. Choose an x value, plug it in, and you'll get a point that solves the original system. Okay, so this is called a dependent system, infinitely many solutions, and here they are in set notation.